Okay, let's do DrC number 1 from homework 8. So this is a problem where you have a track that has quarter circular sections and connected by a flat section. A block of mass m starts at the top of this quarter section, which has a radius r. And one thing you should note, if this is a radius r, then this height is also r, because the radius tells you how high up you are above the bottom of the track. Okay, so the height of this mass is initially also r. Okay, there's a flat section of length L, and when you release the block, this section is frictionless, so it just slides down here and gains velocity. Then it hits a section of the track with friction, so that's going to slow it down. The friction will do negative work, but you're told it gets past this section, then climbs up here to some height h, and you're asked to solve for that height h. Okay, well, the first thing to do is to recognize that your only hope of solving this problem is to use energy concepts or work energy concepts. There's no way to deal with the forces that are changing constantly. Well, there is. It would be very hard to deal with the forces that are changing. The component of gravity along this section of the track is changing the entire time. So trying to use F equals ma would be a poor choice for how to solve this. So let's look at how we'll use energy. Okay, we can use the idea of conservation of energy and say that the final energy, whenever you're up at this final position, we'll call this final for now h, because that's what we're interested in solving for, equals the initial energy, which is energy you start the block with up here, plus any work done by non-conservative or external forces. Well, that's how we'll take into account friction along this section. We'll say plus the work of friction, realizing that friction will be negative work, but in general, you could be doing positive work at increasing the energy. So this is the expression for conservation of energy that I've suggested you use. So now we have to look at all the individual terms. Okay, what's E final when you're at this height? Well, to settle that, I have to first define where I'm going to choose gravity to be 0, and the wisest or best choice is to say, well, the bottom of the track will make gravity equal to 0. You don't have to do that. You could pick it here or there, but then you'd have a slightly more, not difficult really, but more annoying math to do. So we'll pick gravity 0 at the bottom of the track, okay, which means that the final energy you have here, well, energy in general is kinetic plus potential, but this is stopped when you reach that point, and it stops momentarily at least. So the final energy is purely the potential energy of gravity, or mgh. Okay, how about the initial energy? Well, that's also purely the energy of gravity, because you start it with 0 velocity, and that's mgr. And I use r because the height of the block, since it's at the this edge of a quarter circle, the height of the block is also r, and there's no kinetic energy initially either, or else you'd have to put that in, plus the work done by friction. Well, the work done by friction is, let me just write, okay, well, just write, will be negative the force of friction times the length of the path that it travels, okay, and the force of friction we know is mu kn, and the normal force, now you could draw the free body diagrams, etc., but hopefully you could see that whenever the block is here, the normal force will be equal to mg, so that's just mu k mg. Okay, so we have to plug in for the force of friction this, and our expression then becomes mgh equals mgr minus mu k mgl. Now we just do a little algebra and simplify this. First of all, let's cancel out all the m's because they appear in every expression. And actually, we can also cancel out all the g's because they appear in every one of these terms, I should say. And so we see that the height equals r minus mu kl. And that is an expression for the final height h in terms of the things you're given: the radius of the quarter circles, the coefficient of kinetic friction, the length of this horizontal section of track, and that's our answer. So just circle it. Now the next thing you're asked for, B, is if this thing, well, it stops temporarily here, but that's going to slide back down. So hopefully you can see that it's just going to move back and forth, but slowing each time. Okay, as it moves across the section with friction. So each time it goes across this, it goes up to a slightly lower height, and eventually it's going to stop because of friction. So the question is, how many times does it move back and forth before it stops? And we can actually use our same ideas now. We use E final equals E naught plus the work of friction. But now the E final is where it stopped. When it stopped at the bottom, it has no gravitational potential energy and no kinetic energy, so this is just zero. Okay, what's the initial? Well, the initial we can choose to be where you started it with at a height mgr, and you started with zero velocity, so this is just mgr. Gravitational potential energy. How much work will it lose to friction? Well, it's going to be a term that looks just like this, except instead of passing over that section of track just one, it'll pass by n times. So this will just become minus mu k mg nl. Okay, and we're asked to solve for n in this case, and we see we can simplify this expression too by canceling out the m's and g's, and we can solve for n. N equals r divided by mu kl, and that's what we're asked for. Okay, now let's not just stop here. Let's just think about it. In fact, you're told to think about it a little bit. You said to check if your answer makes sense if the friction goes to zero. I'm sorry, yeah, the friction goes to zero. Well, if friction goes to zero, then you've got some r divided by zero, which goes to infinity. That just tells you that without friction, in an ideal physics world, the block would just keep oscillating back and forth forever, going up to the same height r on both sides. And so that makes sense. That should fit with your intuition. Okay, and it's what our formula predicts. And so if mu k goes to zero, n goes to infinity, as I expect. Okay. Another thing I might point out is that there's a temptation when you see this problem to say, okay, I want to calculate the height here. Let's say for part A, first thing I'll do is calculate the velocity at the bottom. Okay, and then I'll see how that velocity changes across the flat part of the track and get the velocity at the end. Then I'll use that to get how high up it goes. So I could solve this problem in stages: first stage, second stage, third stage. And you can do that, and you can do that correctly. But actually, one of the benefits of conservation of energy, or energy principles, work energy, is that you can ignore the intermediate stages of the work and just start here and there and be done, or start here and where it stops and be done without worrying about all the intermediate stages. Okay, so a more efficient way to solve the problem is just define your initial energy and your final energy or final positions wisely. Okay, and you'll save yourself a lot of time and effort. So that's it for Dr. C number 1.